we go. Okay. Um, well, welcome to CISP 310, which is, I cannot even remember the name of the course anymore because it was changed, and I did the changing from assembly language programming to, let's see, computer architecture and organization. That's it. Okay, that's the new name. And it's a very important change of the name because it is not as much about assembly language programming anymore, and it is more about how the components inside the processor are organized. Um, in other words, where this class used to be more computer science, more CS, now it is leaning a little bit more to CE or computer engineering. Um, and you probably have some idea of why computer engineering can be important in the near future. Now that Nvidia is what, a $4 trillion company, and it was only about what, last year that it was a 2 point something, not even $3 trillion company. And a lot of people do not understand how much money 4 trillion is. You can basically operate, you can purchase and operate about 40 aircraft carrier groups. We are not talking about some other countries, Navy. We are talking about the United States Navy, top of the line aircraft carrier. You can have 40 of those things. That's how much $4 trillion is. Anyway, so I'm going to rely on you to read the syllabus, so I don't have to kind of use class time to talk about things that most people would probably know already about classes. But do read that ahead of time, just so that you know the expectations of I don't think I have any really unreasonable expectations, but it's good to check that. Second thing to basically housekeeping stuff is prerequisite. So you have to have taken CISP 360 and pass with a letter grade of C or better in order to stay in this class. Okay. So if you took CISP 360 in this particular district and you pass with a letter grade of C or better, I would have known it already and I would have cleared you of this requirement. On the other hand, if you have not taken that class or you have taken that class from a different college or a different university, then you need to file what we call a prerequisite challenge petition. The instructions are all in this quote unquote homework assignment. It is due on the 27th, which means anyone whom I cannot clear automatically and did not submit anything to show that that person is in the process of challenging the requirement, those people will be dropped from this class. Do we have any questions about the prerequisite of this class? Okay, all right. Then we're going to move on to my YouTube channel. So this is a link to my YouTube channel, and I have years of recording for this class. It is probably more useful just to check out a few videos from the last previous semester, okay, because I do change the way I teach the class, like over time. So, go ahead and check out that channel. And since I'm recording right now, that recording will be uploaded to YouTube within, I'll give it like 15 minutes. After this lecture is over, then I'll start to upload it like right away. So you will have access to the lecture recording, at least within the same day of the lecture. Okay, which is not to say that you do not have to be here in person, because I think being in person is different compared to being online, and I choose to teach in person for all of my classes. All right, so starting this year or this semester, I have a new teaching assistant. So I'm using ChatGPT as a TA for this class. It will have the same knowledge files as what you have in terms of the reading material. So that means whatever I'm teaching in this class, the teaching assistant would also have quote unquote the knowledge of that material as well. So if you want to have a more conversational kind of interaction with the material that you need to read, you're more than welcome to use the teaching assistant. When you're doing your homework assignment, you can use the teaching assistant as well. The lab, for this class, we won't have actual homework assignment for coding until much later in the semester, like halfway through. So for the first half, we're just gonna have labs. But if you want to have more practice, like, okay, I need to make sure that I am understanding the concepts, the TA, ChatGPT, basically a bot, is not a bad resource. You can actually ask it questions. It's like, okay, I want to make sure I understand the material of module blah blah blah. Can you generate a few questions, so that I can check my understanding? It would do a pretty good job. I've tried it already. All right. So do we have any questions about, all of these housekeeping items? We are not quite getting into the content just yet. Nope, we don't have any questions. Okay, so I'm gonna double check, because I wrote down the agenda because I tend to forget what I'm supposed to do. So this way I don't forget. All right, so we got syllabus, we got the prerequisite. So role taking, okay, so I do take role either directly or indirectly. And since we have a lab right after this lecture, basically we're gonna have a lab after every lecture except for like maybe two or three in the whole semester. So I'm gonna use lab activity participation for role taking purposes. So this way I'm not taking roles separately, but sometimes I might do that too. Okay, so today I'm just gonna use the lab activity participation for role taking purposes. I just talked about the chat GPT teaching assistant, so that part is all done. So now we can actually start with the content of this class. Okay. Um, you might want to take notes, okay, during this process, because there are certain things where, while you are listening to me and watching the screen, you go like, I get it. And then 3 minutes later, you go like, what did he say? So you might want to have a piece of paper, just so that you can jot down some notes, particularly about how to use the software that we're going to use. Okay, so if you end up having nothing to write down, you're getting everything. That's good. But just in case you have any item that you want to jot down, having your notebook ready to take notes is going to be handy. All right, so with all that said, I am going to get started. So I'm going to start with the concept of a command line interface. How many people already know what is a command line interface? So we got two, three-ish. Okay, all right. So I'm going to start with a command line interface on this computer. Well, okay, okay, let's do this inside the virtual machine. Okay, so I'm gonna do this inside the virtual machine, which is vdi.losrios.edu. Because I'm using Linux on this machine, so a lot of the command line stuff that I do here may not be directly applicable to you if you're using Windows. So just to make this a little bit more user friendly to people who are using Windows, I'm going to use that. All right. So I'm going to pick ARC, BCS should be fine. So when you're doing your lab after the lecture, you do not need to use this particular interface. Okay, you can just use um, the computer that's in front of you, because those already have the software installed. And okay, so we'll just wait for this virtual machine to boot up, and then we'll take a look, at how to use a command line interface in Windows. How many people are using a Mac in this class? Okay, so do you already know kind of how to get around on a Mac? Okay, all right, excellent. All right. Anytime now. Well, it says it's running, so not sure exactly why it's hesitating. All right, if this is not working, then you kind of have to read the instructions, and kind of do it that way. All right, so if that is not working, I am going to use the command line on my own computer, which is going to look a little bit different. Okay, so this is what mine looks like. It is Linux. Mac OS is very close to Linux, so people who use Mac, can pretty much transfer what I do here, to what you need to do. All right, so this part you don't want to write down because I wrote a script to do this. So Logisim is the name of the program. In the lab instruction, it will tell you where to download it and how to get it started. So don't worry about not knowing how to install it. Oh, there we go. It's just kind of slow. Okay, well, that's okay. All right, so where's my toolbar? Or there we go. All right. So in Windows, in order to start the command line interface, you type CMD. Okay, so let me start the whole thing again. You go to here. Okay, this is actually the fastest way is to click on the little search bar here, type in CMD for command, and just click on command prompt. So once you click it, it will give you this little box here. Okay, this is what we call the command line interface. So with this, you can now check whether you have Java already installed. So if you just type your java-v, I think, okay, well, it is installed. Could not create because, okay, that's dash version. There we go. So we do have Java already installed here, so that's good. And then the next thing we need to do is to download Logisim, and the instructions to do that is already in the lab description for today's lab. So, we don't have to do it over here, but I just want to show you what the command line interface looks like here. So now we're switching back to my own command line interface, which is not the same as what you're seeing here. And since I have already written a script to start up Logisim, it's more convenient this way. So we just start it up. All right, so let me move that screen over here. So what you're seeing here at this point is called Logisim. It is going to be the program that you'll be using for the rest of this entire semester. So this is the tool that we are going to use. The main purpose of Logisim is to design circuits and to simulate the circuit so that you can actually say, oh, okay, so this is how the circuit is going to work. And we are going to start with this today. Okay, so I'm going to defer the discussion of the theory behind the circuit to Wednesday, and then we'll focus on what we need to do today in the lab. Okay, so it's more interactive that way. So there are a few key concepts that we have to understand in order to use Logisim. On this side, you have all of these, kind of like folders, and inside each folder, you have some additional items. And this is basically, the items that you can put into the circuit itself. So think of these as classes in object-oriented programming. And, okay, I should say, these are classes. And if you want to, let's say, make a constant, you click on it, and then you just move your mouse, not dragging. This is just moving your mouse on the other side, and then you click it. So this is basically an object of this particular class. You can change all the attributes of this particular object. Okay, so we're gonna delete this one because it's not exactly the one that we need. All right, so this is how we place components. Choose components on this side and then place the component onto this side over here. If you have a laptop computer and your screen resolution is really, really high, then you can also change the zoom ratio over here. So right now I'm at 150%. I can zoom in or I can zoom out. Okay, 150 is just about right deal for a class. So I'm gonna stay at 150. Do we have any questions about the application itself right now? Okay. Yep, go ahead. So the that instruction is in the lab instruction itself, so there's no need to worry about it. I in the instructions in the lab, I will give you a link, so you just download it, and it will also tell you how to use the command line to start it up. Mhm. All right, so at this point, I'm going to first introduce the two kind of most elemental components of Logisim, and those are pins. So you can basically get a pin from here, but you can also get it from here. There are two different pins. This one with a square is called an input pin. This one, that has a circle or the outline is a circle, is an output pin. So they are basically doing exactly the same. Um, they're performing the same tasks as pins on the circuit board. An input pin means, oh, you can connect the input pin to a high or low voltage. And then the output pin means, somehow the circuitry is going to decide the voltage, but the output pin is kind of like the output of the entire circuit. In terms of functions and terms that you already understand from CISP 360, the input pins are like parameters to functions, and then the output pins are like the return value from a function. Is that analogy working? Are we good? All right, sure. So the input pins are like parameters that they're like parameters of a function definition, and then the output pins is like the return statement of a C++ function. Are we good? All right. So we're gonna make one rather kind of stupid circuit. So we're gonna pull an input pin. We're gonna pull an output pin. So when I said pull, it really is just click here and then move the mouse over here. Many of you may be tempted to use this pin. Do not do that because these two pins are special. They are configured, correctly to be used in most of our circuits. So do not use this one, but instead use the ones on the toolbar. So in order to make a connection from one component to another component, now some components have more than one what we call ports. Okay, so when you hover your mouse pointer over a point and it changes to a circle, it means it is a port. Some components, like an input pin, only has one port. But other components like a logic gate may have more than one port. Okay, so a component can have multiple ports, and then you have to be careful which port you're using to make a connection. Okay, so in this case, this is a port. So when your mouse pointer displays a circle, that means if you were to drag it here, then it would be dragging a line or wire directly from that port, and then you can just make a connection to the other port. So now we are directly connecting an input pin to an output pin. Now, once you have a tiny little circuit like this, which really doesn't do much, you can still do something with it, okay? You can still interact with it. You can see how I'm using the pointer tool, okay? This is called this edit, selection, and add wire tool. This is called the poking tool, okay? I'm pretty sure it has nope, change value within circuit, but I just call it the poking tool. So you can change to the poking tool if you want to interact with the circuit. So now I'm not editing the circuit, I'm trying to interact with it. So with the poking tool, you can now click on an input pin to toggle its state. All the input pins are binary, which means it can only be a 0 or 1. So whenever you click on an input pin using the poking tool, it will just alternate between the 0 and the 1. Are we doing okay so far with that? Okay. So in this particular circuit, it is not really surprising that when the input pin changes to a 1, the output pin also changes to a 1. When the input pin changes back to a 0, the output pin changes back to a 0 because they are connected directly. Do we have any questions about this? Questions? All right. So before we get to the more tricky stuff, okay, which is a transistor, I'm going to introduce the concept of a multi-bit pin, okay? So we'll go ahead and sever the connection. So to edit the circuit, you have to go back and use the pointer tool, and then you just point to the object that you want to work with, like this. Do a click, and now you can see it is now selected. Then you can press the delete key to get rid of it. Okay, so fairly standard way of interacting with a GUI tool. Single click is to select. You can also do control click to select multiple items, and then pressing the delete key will get rid of it. Okay, I believe copy and paste is kind of the same. Control C, Control V, would do what you would expect it to do. So now we're going to do something a little funky here. So I'll click on this particular input pin, okay, because I want to change it. When you click on an object, the properties of the object will be displayed here. So now we can see that for any pin, there are these attributes. There's facing, which is really just controlling the direction of the port on which side is the port. So by default, it is on the east side, but you can change it to north, south, or west. Okay, so that means you're basically rotating the input pin. That really is for the most part for display purposes. The second one is called output with a question mark. So that means it is a Boolean value. It's either yes or no. This is an input pin, and that's why it is not an output pin. Data bits. This is where we get a little bit interesting. So right now, this particular input pin can only be used to specify one bit or one binary digit. You can change the number of data bits so that it is more than just one. So when you click on this, it is a drop-down box. And let's just say that we want this to be a 4-bit input pin. Okay. So now you can see how the diagram or the display is now changed to 4 digits. So that means it is equivalent to looking at the header of a circuit board. Do you guys know what is a header? No. Um, they are rows of pins so that you can connect using the cable. You can connect another circuit to the circuit that you're working with. Okay, so now it is kind of like having 4 different individual pins, and each pin can only be a 1 or a 0, but it is kind of grouped into one at this point. Are we good so far? All right. So there are 4 of these, and there's only one of these. So that means if you are to draw a connection right now, Logisim is not going to be happy about it. It will give you this. Hello. So with this, you can read the message down here. It says incompatible with, because this particular port is a 4-bit port. This port here is a 1-bit port. They are not compatible. When you draw a wire to connect 2 ports, they must have the same number of bits. Is that okay? So you go like, okay, so how do we fix this problem? The first question is which one, okay, in this case, you can ask which one of this particular 4-bit input pin do I want to connect to this one single bit over here. Now, you can also change this one and say, okay, I want 2 bits out of here. Okay, I'm just arbitrarily choosing 2. But you still have that question. It's like, okay, but which 2 of the input should connect to the 2 bits of the output? So you still have to make a choice there. So to do this, you cannot just use a wire. A wire does not give you the ability to choose and kind of splice, so to speak, splice the pin. So what you need in this case is what we call a splitter. So let me uh, pick a splitter here. So a splitter is right here. So a splitter looks like this. Okay, by default it looks like this. So the first thing is we're going to take a look at the attributes of a splitter, and then we'll take a look at the ports of a splitter. So once again, we have a facing. So east is the split end. So a splitter has 2 ends. It has a merge end, which is the single end over here. This is one. And it has a split end where you can have a number of wires coming out. Okay. Does anyone know, what is that a cable can have multiple wires inside it, multiple individual wires inside a single cable? Is that concept okay? We good? All right. So this is basically the same thing, like, on this side, this connects to the one single cable, but it can split the individual wires into multiple cables on the output side. Is that concept okay? All right. So it's kind of like a map. Okay. So now we want to look at the second attribute, which is fan out. Fan out means how many split ends do we have? And then we also have bit width. Bit width in is specifying on the merge end, the combined end of a splitter, how many bits do we want to specify? Now, because we want that combined end or the merged end to connect to here, we want to change this to 4 in this case. Are we good so far? All right. So now, but what about this one here? There's only one end over here. So we want the fan out to be 1. In other words, there's only one input and only one output. Okay. But then we still have to decide which bits of the input pin connects to the bits of the output pin. So I'm going to write something on this circuit here just so that I remember. So you can use the text tool. It's just typing. So we'll go ahead and say, bit 0 of the output should get, the last, the most significant bit of the input. And then we want the second bit of the output to get the first bit of the input. So I'm using the array syntax to designate, the individual bits of the input pin and also the output pin. Is that notation okay? Does everybody understand the notation? All right. So I'll leave the text here. So now we have another question, which is, so which way do we do the counting? In other words, you look at the input, you go like, okay, but which one is input 0? Which one is input 1, 2, 3, and well, it's just 0, 1, 2, 3 because that accounts for all 4 positions. This is bit 0. This is bit 1. This is bit 2. This is bit 3. It follows the very same convention that you write numbers in base 10. Okay, the least significant digit, which is digit 0 or bit 0 in this case, is the rightmost one. The leftmost one is the most significant digit. In this case, it is digit 3 for the input pin. Are we good with those terms so far? Okay, all right. So according to this is what we want to do. So now we go back to the splitter and we go like, okay, so bit 0 of the input, okay, bit 0 of the input is supposed to go to bit 1 or the top of the output. So that is correct. And then we also have bit 3 of the input. So these two are not connected. If they're not connected, that's all you need to do. You simply say that they're not going anywhere. Okay. So now we have, well, actually, we have to reverse those two because right now, okay, let's go ahead and take a look at what happens when we make a connection here. It's not quite what we needed to do, but close. So now we make a connection from here to here, make a connection from here to here. Oh, come on. There we go. Okay. Looks like it's working, but it's not. Because what this is doing is bit 0 goes to this bit 0 here, but bit 3 here is also going to this bit 1 over here, which is not what we want according to the text. So let's double check, okay? I said that is not what we want, but we'll double check. So bit 0 goes to bit 0, which is already wrong, because according to this, bit 0 of the input is supposed to go to bit 1, which is the leftmost bit of the output pin. So this is definitely not doing what we wanted to do, but it's choosing the right bits. It's just the ordering is incorrect. Are we good so far? All right. So how do we get it to do the cross wiring thing? Well, turns out it is a little bit more complex than we want it to be. So we'll take out, this component, take out all of these extra wires, because we actually need 2 splitters to do this. So we'll go ahead and take a look at how do we use 2 splitters to do this. So we take 1 splitter, 2 output is good. Input bit width is going to be 4. In other words, we're taking something that will give me 4 bits, but we'll break it out, to the individual bits. Bit 0 of the input will make it go to the top. Bit 1 and bit 2 are not used, so they are none. And then bit 3 is the one going to the bottom. So that's how this splitter ends up looking like this. Okay, so we'll go ahead and make a connection here. So right now you can test it too. So even though I have not connected the split end of the splitter to anything, you can test it out already because dark green over here means a 0, light green means a 1. So that means if I use the poking tool to poke bit 0 here, I should see the top one, changing color like that. At the same time, if I use the poking tool again, but this time I poke, bit 3, I should see the bottom split end also changing its color, like so. So are we good so far? So this is really useful because it means you can actually take a look at the coloring of a wire and be able to tell its value if it is already a single bit. Is that okay? All right. So now on the other end, now we have to go like, okay, but somehow we have to combine these two into one single end here. So that means now we need another splitter. So we pick out another splitter. It also has a fan out of 2, but it also has a bit width output in this case of 2. So that means we are going to change the facing to kind of turn it up, like this. Okay, so we'll put it over here like so. Okay. So this time we kind of know what to do with this because we want bit 3 of the input to go to bit 0 of the output. Okay, so we'll test this first. This is bit 3 of the input. This is bit 0 of the output. Toggle this. Aha. Okay, so that now it's doing what it's supposed to. So now we have to connect this particular port to this particular port here. You have a few options. If you don't want anything to cross, you can kind of go all the way around it. Okay, that works too. Ah, come on. There we go. So this circuit is functional because if I toggle bit 0 of the input, bit 1 of the output, it also reflects the state. But what if you don't want to get a wire to go all the way around something? Well, it's actually easy. Okay, so you can actually I'm going to take out the wires that are not really needed. Okay, so take this out. And you can take out the wire one segment at a time. So now what I can do is now I can just go like this. This also works. So if I toggle, you can see how the correspondence is still correct. This is because when you look at this particular junction here, it is a flyover. A flyover means if you think of this as the road or the highway, this means you have one highway that is an overpass of another one, or you can say the other one is an underpass of the other one. But basically, you can have cars going on one. It doesn't change anything with the other path. Is that okay? There are occasions where we want a real intersection, okay, where the wires are actually connected. So I'll describe how to do that later. So are we doing okay so far with the concept of input pin, output pin, splitter, and how you configure each split end, using the property of a splitter. Okay, great. So let's just say that by the time you do the lab, you have completely forgotten what I said. So what are you gonna do? Well, you can raise your hand and I'll come over and help you out. Okay, that's the whole purpose of having an in-person lab. But you can also use a resource that is built into Logisim. Go to help, go to library reference, and let me drag the reference window. Okay, there we go. There we go. So the library reference has an organization that is very similar to the tool bag that you have in Logisim. So now you go to wiring, And when you get down to wiring, you can see splitter is also the first item in the help in the library. You click on splitter and it will explain away, what it is, how do you configure it, and so on. So that means, if you have questions about the individual components that you need to use, the online help is already built in. Are we okay so far with that? Okay, so you know where to find the extra information. All right, cool. So now we are going to do something a little bit more interesting. So we're going to start to introduce components that actually get something done. I mean, this is not a really useful circuit. All it is to scramble the bits of the input to the output. That's all it's doing. Okay, it's not very interesting. All right, so if this is not so interesting, we're gonna get rid of the items or some of the items. You can also use drag to select an area to select multiple things at the same time. Then you can press the delete key to delete all of them at the same time. So it's just kind of handy, but you know, that's just a handy feature. We're gonna need the splitter at some point, so we're gonna stash it to another side. My mouse control is kind of questionable because it's not a mouse that I'm using. I'm actually using an IBM touch point, so it looks like a little eraser on the keyboard. So I can push it one way or the other. It controls the velocity of the mouse pointer moving in that direction. So it's kind of indirect, but it's nice. Okay, let me show you what I mean by that. This is my keyboard. This is called a touch point. So it does not move, okay? You basically push it in a direction and then the mouse pointer on the screen will move in that direction. The harder you push, the faster it goes, and so on. I can actually play video games with this. My kids, when they were younger, they were they were just shocked by, dad being able to play video games using just the keyboard. There's no mouse. What do you mean by you need a gaming mouse? You have a keyboard. Alrighty. So now we're going to make an actual circuit. Okay. So this circuit makes use of transistors. So I'm going to take a transistor and just kind of stash it on the screen and kind of magnify the screen a little bit. So this way I can take a closer look at the ports of a transistor. And you can see that when the transistor is selected, it will also give you the properties of the transistor. Two of these properties is really just for display purposes and it's not really super important. So we'll talk about those first. The first one has to do with phasing. So that's just the orientation of the transistor. By controlling the phasing property of a transistor, east, south, west, and north, you can rotate the transistor. Okay. The other one is gate location. There are three ports to a transistor. The gate is this one here. So it's pretty easy to tell which one is the gate because the gate is the one that cannot be confused with the other two. Okay, so that's the gate. So right now the gate position is top, or if you rotate it, it'll be on the left. So if this makes your circuit looks ugly, you can flip it, you can rotate it until it looks good. Okay, but it doesn't change the function or anything else. It doesn't change anything functional about the transistor. All right. So that means the other two is going to change the functional property of a transistor. With your homework assignment or your lab, you're going to stay with one single data bit. Okay, so that means we have already addressed three of the four properties. The only property that is kind of tricky is the type. This is called a p-type transistor, and the other type is called an n-type transistor. So you can kind of toggle between these two, and just kind of go like, okay, so what is the difference? The little bubble, right? So with an n-type, there's no bubble here. And then with a p-type, there is a bubble over here. So is it really just the display of this, or is it actually functional? So as it turns out, with transistors, the three ports are interrelated. Okay, So for this part of the lecture, I am going to have to, I'm going to use some test circuits for this, okay, just so that it is easy to tell, which way or how to use the transistors. You can see there's an arrow here. So whether it's an N or P-type transistor, there's always a little arrow here to tell you which port is the source and which port is the drain. Okay, and I intentionally did not tell you the location of which one is the source and which one is the drain because I want you to think about it and come to and guess. Okay, I know I haven't talked about it and the class material has it, but we haven't really gone over that either. So if you are to guess which port is the drain and which port is the source, the left versus the right. Yes, the left is the source and then the right is the drain because the flow goes from source to drain. Okay, so you're correct. So now we have identified all three ports of a transistor. This is the gate, and in certain components it actually tell you the name of the port, but not this one. This is the gate, this is the source, and this is the drain. Okay, well, but those names are not really particularly useful. So what do you think the gate is doing when the other two ports are named source and drain? What is the name gate usually associated with? Yep, that is correct. So the gate specifies whether we are allowing flow from source to drain. In other words, this is a valve or an on-off switch, if you will. Is that okay? The switch itself, the toggle, is the gate, which is the one on the top, and then whatever stuff is flowing is going from the source to the drain. So the gate specifies whether the flow is allowed or not, whether the valve is open or closed. Is that okay? All right. So what kind of stuff is flowing in this case? Well, this is in a circuit, right? So we can kind of expect that this has something to do with electricity. So this is the part that gets a little bit tricky because let me rotate this a little bit just so it looks correct. There we go. Okay. So with a P transistor, the source should always connect to quote unquote the high voltage. So in terms of high voltage, it is called power. So in the circuit, power specifies where the source voltage is. It's kind of like the plus terminal of a battery. Okay, so power always connects to the source of a P-type transistor, and then the other end is connected to something else. Okay, it can be a light bulb, can be a LED, stuff like that. And if you want to play with LEDs, I think it is actually in input output. I'm not sure whether it's going to work here because a typical LED needs a little bit more than that. Um, we'll just go ahead and hook it up like this, and then the gate controls whether this whatever the positive voltage can flow through the transistor to the drain. All right, so now we're gonna have another input pin, okay, just so that we can play with the transistor. Okay, so here we go. So we can see how the flow is on right now, how the high voltage, okay, how the high voltage is going from the source to the drain, and that's why the drain is also now in bright green. So as in the case of a P-type transistor, when the gate voltage is significantly lower compared to the source voltage, it is on. Let me say that one more time. Okay, with a P-type transistor, when the gate voltage is significantly lower to the source voltage, it is on, which means it allows flow. Are we doing okay so far with that? I will just type it, okay? So I can take my own notes and put it here. but you might want to put it in your notes too, or at least note the time. So this way you can go back to the video and go back to that time frame and go like, okay, I didn't have time in class to write down everything, but I know what the time is. So you can always fast forward in the video recording and go like, okay, I need a screenshot at that moment. Okay. So I'm gonna write this down. Okay. So with a P-type transistor, um, on or yeah, on. Okay, I put it the other way. Having the gate voltage less than the source voltage means it is on. There we go. So now so this diagram right now confirms that claim. So you're just going to take that claim and go like, okay, since tech says that, that has to be the case. I don't know about your other professors, but that attitude will not be helpful in my class. Okay, you always want to doubt what I said. Okay, so in your head, you need to go like, okay, but how do we make sure that what Tax said was right? In other words, what if the gate voltage is the same, not less than, but the same as the source voltage? I need to observe something to confirm that the transistor is going to be off, right? So because your Logisim is in kind of like a really nice lab setup that is virtual, you can just do that, right? Toggle this input pin so it is a 1. So you can see that when it's a 1, it is now the same as the source voltage. It's not less than anymore. And then the output is now in blue. What does it mean if it is blue? Blue means it's not connected to anything. Okay, which is also known as a floating state, but it means it's not connected. The whole point is the source and the drain are not connected. You are not allowing anything to flow from the source to the drain. Is that okay? So this is the behavior of a P-type transistor. So the next question is, okay, if there's a P-type transistor, what was the name of the other one again? The N-type, that is correct. So now we're going to design another circuit to test out, okay, what about the N-type transistor? What does it do? So with this one, I wanted to point north, okay, like so, and then change the type to N, okay, like so. So with an N-type transistor, okay, I'm going to stash a circuit here. It works kind of the same way, okay? It works in the same way in the sense that the gate is going to specify whether flow is allowed from source to drain. So that particular aspect of the transistor is exactly the same whether it's an N or a P type. What is not the same is what is flowing here. In a P-type transistor, it is a positive charge that is flowing. In other words, you're specifying, am I allowing a high voltage to travel to a low voltage? With an N-type transistor, it is exactly the opposite. You are basically specifying, am I allowing negative charge going from source to drain? So one easy way to remember is the name of the transistor itself. A P-type is controlling the flow of positive, right? Positive charge. And N-type is controlling the flow of negative charge. Okay, so that's why they're named, well, sort of. That's why they're named P and N. Okay, there's actually a little bit more to it, but you can kind of use that to remember, what it is switching. So the infinite source of negative charge is called ground. Okay, so this is the ground symbol. So that has to connect to the source of an N-type transistor because it is specifying whether negative charge can flow or not. So that source has to connect to an infinite source of negative charge, which is known as the ground. Okay, which is also kind of like the negative end of a battery. Okay, so now we say, okay, so Tack, you said earlier that the gate is also controlling whether flow is allowed or not. So how does it work in this case? So I'm not going to say anything. I'm just going to do the experiment. Okay, so make a connection. So let me ask you, according to the coloring of stuff on the screen, Is the N-type transistor allowing flow or not? It is not. Very good. Okay. It's not allowing flow because the the drain is of a different color compared to the source. If it was allowing flow, they should be the same, which is dark green or zero in this case. Okay, so very good observation. So now we toggle that gate or the input to the gate and see if a high voltage of the gate is going to turn it on. And sure enough, when the gate voltage of an N-type transistor is greater than the voltage of the source, it is allowing flow. And we good so far? All right. So now, instead of typing everything from the beginning, I'm just going to do the super lazy thing, which is copy and paste, copy, paste, and move it around a little bit. There we go. And if I click here again, I can actually change it. So now I can say for an N-type transistor, when the gate voltage is greater than the source voltage, then the device is on. This is N, not B. There we go. All right. So I just took a little bit of notes for you. Okay. But this is the sort of things that you might want to write down in your own notes. Are we good so far? All right. So I'm going to digress a little bit to kind of talk about why taking notes is important. Okay. What do you think is the retention time of your short-term memory? In other words, if I give you like a phone number or even just 4 digits, okay, this is the 4 digits to the padlock of my house, okay, and I give you 4 digits. How long do you think you can retain those 4 digits in your head? Yep, seconds. Okay, it's measured in tens of seconds. And that's without distraction. That's without me saying, oh, look at this color here. Oh, light green, bright green, dark green, blue, blah, 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 and so on. So with all the other stuff, and these are new concepts that you're learning too. So it's not like oh, okay, I learned about this, like 2 semesters ago from electronics technology. This is just a review. I got this. Okay. No, no, to most of you, this is new, right? So you got new stuff, new concepts. You're trying to make connections between the concepts along with the terms that you're learning, right? So a lot of stuff is happening. You can probably bet on that retention time down to 15 seconds or less. Okay. So at the time, I know you guys are smart, okay, because otherwise you wouldn't be in CISP 310, you will still be in CISP 360. So I know you're smart. You can comprehend what I'm talking. You can nod. You can tell me that, okay, I got this. Understanding does not mean it is sinking in. Okay. Which means, at the end of the lecture, if I ask you, so what did you learn? You go like, not really sure. Okay. But you understood everything when I was talking about it. Okay. So the fact that you're understanding all the stuff is good. Okay. That means you're comprehending, you're understanding, but you still need some mechanism to help you remember, to retain that information. So now the next question is, but I thought all this stuff is recorded, so I just go home and rewatch the whole video. I'll be fine. Well, sorry, go ahead. Yep, we're going back to the 20-second thing. So as it turns out, the circuitry in your head, okay, in your mind, when you are listening to something, when you're reading something, when you're writing something, and when you're talking about something, they all exercise different portions of your brain. So that means when you're listening to me, it's using one pathway. But when you write your notes, it's using a different pathway. So that helps you retain that information. Okay. Now, if after class, a few of you get together and then you're trying to explain the concepts to each other, you're talking about it, that's using another channel. Or if you read the material ahead of time or afterwards, that's also using a different pathway. So when you use multiple pathways to access the same connections, the same concepts, you have more pathways in your head to connect those things. So it's easier for you to remember, to recall what you have learned. So that is one reason why we take notes. It's not because, oh, okay, the teacher says, when he was a student, he took notes and he's making all of us to take notes too. No, it's not because of that. It's because it is a mechanism that actually makes sense. There are also studies, to say that if you write notes, like using a pencil and you actually do handwriting, it is more effective than when you're typing. The reason, okay, now this one is kind of controversial in a way. The reason why it can be more effective for certain people is you simply cannot write as fast as you can type. So what do? You actually have to think about, okay, I got all this stuff to write in this much space. So now you have to actively think about, how do I compress this much stuff into only this much space on my notes. That whole process of compression also gives you another pathway. Okay, it is exercising another portion of your brain, because now you actually have to understand what you're trying to write so that you can compress it. You cannot compress something if you don't know what it is. So I'm telling you all of this because I just want to emphasize study habits that can be effective, especially after you leave here. If you think the classes here are difficult, well, I'm gonna say you'll be surprised. All right. So enough of that stuff. So now we go like, okay, so now we have a pretty good understanding of transistors and N-type, P-type, and stuff like that. So where are we going with all of this stuff here? Okay, in other words, what are we getting at? So I cannot fault anyone for not reading the notes ahead of time, because it is the first class. So, but in the future, it is always going to be helpful to read a little bit ahead of class. Um, but it's the first class, right? I fully understand that. So now I'm going to build a circuit. So I got power over here. I'm going to pull two transistors. Okay, so I'm going to also kind of give you some cool tips to how to do this. I want this to face south, and then you can type Control D to duplicate. So this is Control D. It duplicates the components that was selected. So and I just move this one over here, and I want it to look nice. So I'm gonna flip the gate position to the other side. Now for the lab, you don't have to make it look nice. Okay, I just prefer to make it kind of more or less symmetric like that. And then I need two more transistors, and both of those are going to be N types. So I'm going to do this. Select both of the P-type transistors, Control D to duplicate both of those, kind of move it out of the way down here. And I can flip both the types of both of these from P-type to N-type. So Logisim looks at whatever you have selected, and it will reflect things that are common to both of the components, or all of the components that you have selected. So because I have selected two instances of the P-type transistors, so the type as well as the phasing and also the data bits, they're all universal. They're the same. But gate location, they're different because I changed them. So this is one really kind of cool thing that you can use to kind of, it's not a big deal, but I can change the type of both at the same time to N type, and at the same time I can flip them to point north at the same time. Now, is this really necessary, these little tricks? I would say no. Okay, it does help save you a little bit of time, but it's not 100% necessary. But I'm showing you what you can do with the interface, just in case you have a lot something that's a whole lot more tedious to create. So now I put this here, and this one I'm going to flip it back to the other side. So I'm going to flip it back to here, and I'm going to put it over here, and then I need a ground. Stash it over here. I need So in this particular design, I'm going to use two input pins. Your lab is going to call for something different. Okay, so do not just replicate what I'm doing here. Make sure you read the instructions of the lab. All right, I'm going to have one output pin out of this entire circuit. I'm going to stash it over here. All right, So now I'm going to make some connections. Remember, do not just kind of drag from, like, if you try to drag from here, oh, okay, it won't even let me do that. But, unless your mouse cursor um, causes the circle to appear, you are not specifying a port. Okay, so make sure that you only make connections from a port to another port, to a port to another port. And you can see in this case, there is a solid circle where the junction is, because in this case, it is connected. There we go. And then we have this one connected to here, and then here, and then here to here, here to here. The output connects to this over here, and then this input pin connects to one of the P-type transistor and one of the N-type transistors. This one connects to the other two. Come on, there we go. And then I need this also to connect to this one here. I'm just going to route it over the circuit. Come on. There we go. All right. All right, so now we have a circuit. And I'm going to stop simulation because I want you or us to figure out what it is supposed to do. So I turn off simulation here. Now, if you accidentally turn it off, you would see the circuit like being like this. So when you see everything being blue, you can just go ahead and check whether simulate has been turned off. If it is already off, just re-enable it. All right. So now I want to go like, what is the output supposed to be in this case? In other words, if you look at the circular pin, which is the output, what is it supposed to be? So the way you analyze this circuit is to look at each one of the transistors and figure out, is it on or is it off? Okay, because once you figure out the transistors, then you can figure out what the output pin is actually connected to. Is it connected to the power, which is a 1, or is it connected to the ground, which is a 0? So let's go ahead and check this out. This is a 0 here. It's going to the gate of this particular transistor, which is is that a P-type transistor or is it an N-type transistor? It's a P-type transistor because it's got that little circle, right? So it's a P-type transistor. So with a P-type transistor, is it on or is it off? Is it allowing flow or not? Yeah, right now. Is it supposed to allow flow or not? Yeah, it is. Okay, very good. So it is supposed to allow flow, and same with this one over here. So that means this power, which is an endless source of 1, is connected through both of these transistors to the output. So that means the output should be a 1. But we also want to make sure that the N-type transistors are both off. Well, they're both off because the input or the gate to both of these N-type transistors are zeros. Okay, so if I re-enable simulation, sure enough, the output is a 1. Okay, so let me flip the question around and ask you, if I want the output to be a 0, how do I make that happen? I want the output to be a 0. Yes. Okay, that is correct. Well, this is an AND gate indeed, but how do we figure out what the input pins need to be in order for the output to be a 0? That is correct. So let me explain the steps, and you can tell me whether I'm getting your concept or idea right or not. We want this to connect to ground because that will turn the output to a 0. Is that okay? An output of 0 means the output pin is connecting to ground. And when you look at this circuit here, the only way for the output pin to connect to ground is to follow this path. Okay, chugging along here, And then when you're at this junction, turn south. It has to go through this transistor. So that means this N-type transistor has to be on. It has to allow flow. But that's not enough because you have another N-type transistor in your way before you can get to the ground. So that means both of the N-type transistors, both of these, there we go. So both of these need to be on. In other words, they both need to allow flow. But since they're both N-type transistors, you have to remember, so how do we turn on an N-type transistor? What is the gate? What does the gate has to be in order to turn on an N-type transistor? They have to be ones. So that means the gate of the top N-type transistor has to be a 1. So this has to be a 1. The bottom N-type transistor connecting or where the gate connects to the bottom input pin also needs to be a 1. So that means when both inputs are 1s, the output is going to be a 0. Okay, at least that's the theory. The beauty of using Logisim is you can try out. Okay, so you just go ahead and go like, okay, let's re-enable simulation and then use the poking tool, change both of the input pins to 1s. Aha, that works. Is that okay? So when you look at all the 4 possible configurations of the input and then you look at the output, as you said, it is a NAND gate, N-A-N-D, which stands for negated AND gate. Okay, so I'm going to use a kind of primitive text editor to try to explain this part. Give me a second here. So do we have any questions about how to use Logisim? Any questions about the user interface of Logisim? You guys are okay with that? Okay, all right, cool. All right, so we'll go ahead and name the pins. Okay, so it's useful to name the pins. So I'm gonna go to, I can use the selection tool, click on the pin, and you can see how it allows you to specify a label. So I'm gonna call this X, okay, and call this Y, and then we'll call this, I'll just call it out, okay, OUT. All right, so now we want to create a table of, this is what we know about X, this is what we know, this column is for Y, and then this column is for out. We know that when X is a 0, Y is a 0, the output is a 1. When at least one is a 0, the output is still a 1 because you only need one of these two paths to go to the top end, which is a 1. But you need both of these to be connecting to get to the ground. So that's why when X or Y is a 0, the output is still a 1. So we fill that in. This is also a 1. But when both inputs are 1s, the output is 0 because we just worked that out. Is that okay? So you look at this table here. You go like, well, it doesn't really match anything from CISP 360. Okay, so let me show you what I mean by not matching anything from 360. So we look at Y, X, Y again, and now we look at X and Y. Okay, so this is a truth table. If X is 0, Y is a 0, X and Y is a 0. If one of them is still a 0, the output is still a 0. Only when both of them are 1s, the output becomes a 1. Go like, that doesn't match the circuit. You go like, maybe we should try disjunction or. So now we look at X or Y. Okay, same thing. X, Y are both zeros. The OR is going to be a 0. If at least one is a 1, the output is a 1. And I'm going to turn off a line number because I think it's just kind of interfering with what I want to show here. Okay, so you can see that the 3 truth tables are all different. In other words, they don't match up exactly. But you might notice that the second truth table is the inverted version of the top truth table. In other words, it just flipped all the zeros and ones. Let me point out what I mean by that. If you look at this truth table here, the outputs are 1, 1, 1, 0. given that x, y are configured, in that specific way. But when x and y are also specified in those specific way, the output of an AND is exactly the opposite of the circuit that we're designing. Are we noticing that? Okay, so that's why the circuit that we have designed is called a NAND gate or a negated AND gate. In other words, instead of out here, I can just say the negation of x and y. And that's why it's called a NAND, N-A-N-D. Are we doing okay so far with all of this stuff here? Cool. All right. So now you go like, great. We have just learned a gate that does not correspond to any logical operator that you have learned in CISP 360, right? It's like, why is tech wasting my time talking about something that is irrelevant? There's always relevancy in the stuff that I talk about. The question is, how do you make connections to things that you have learned already? Okay, so now we go like, okay, so let's see whether we can make AND happen using NAND. Okay, so now I'm not going to talk about Boolean algebra here, okay, but I'm going to kind of use just specific cases, okay. So we'll go ahead and create another truth table, okay. The first one that I want to create, let me see, right. So what if I don't even bother to have y, okay. So y is gone. I can't, well, this is not a spreadsheet. I cannot do this easily, but that's okay. I just have to get rid of all this stuff here. What if I only have x, but I'm still looking at x NAND x. So this is doing AND, this is x here. Okay, can someone help me fill out this column? What is the negation of 0 and 0? It's a 1, okay. This is a duplicate, get rid of that. This is also a duplicate. All right, so what about the second row? If x is a 1, 1 and 1 is, no, 1 and 1 is 1, not 1 is a 0. Is that okay? I think I just found how to do negation using NAND. All right, that is kind of helpful. Okay, so once we have negation, you go like, hey, if I have a negation, I can just take this thing and have it to negate itself using the same pattern here. In other words, okay, so I'm going to leave this one to you. So I will give you the template, but I want you to go through the trouble, the chore, the tedium of working this out, okay? Because it is kind of important. So what I want you to do is to look at this as this, okay? This is basically a NAND. What am I NANDing? What I'm NANDing is X NAND Y. Copy and paste. So I want you to evaluate this really clumsy expression and come up with the answer for each one of these rows and tell me whether I have accomplished just regular conjunction. I can work out one row for you guys. Okay, so let's say I work out the third row here. Okay, this is the row that I want to work out. Okay, so you go like, okay, 1 and 0 is a 0, not 0 is a 1. Okay, same thing over here because these two expressions are the same. So we have 1 here as well. 1 and 1 is a 1, not 1 is a 0. Okay, all right, so let's put a 0 over here. Okay, and I think without much explanation, most people are convinced this one should be a 0 as well. Why? Why can I come to that conclusion without even thinking much about it? It has to do with algebra. But Tech, you promised no Boolean algebra. Yes, I did. But this is like really elementary algebra stuff that you already know. What is how do we call that thing where let's see, A times B is the same as B times A, whatever A, B are, as integers or real numbers. How do we describe that property? It's called a commutative law, okay? It works in Boolean algebra too, okay? So that's why I can easily fill in these two. Let's take a look at this one. So I'm going to finish this table for you. So when x and y are both zeros, x and y is a 0, not 0 is a 1, 1 and 1 is a 1, not 1 is a 0. Okay, so we stash a 0 here. So now we get to the last one when both are 1s. 1 and 1 is a 1, not 1 is a 0, 0 and 0 is a 0, not 0 is a 1. Okay, stash a 1 here. Hey, I think that looks like conjunction to me, except it is going through a lot more seemingly unnecessary operations. So are we doing okay so far? All right. So at this point, we got negation, we got conjunction. Okay. So disjunction, which is OR, can also be done using NAND. So NAND is what we call a universal gate because we can use NAND gates to make up and create all of the other logical operators that we ever need in Boolean algebra. All right. So do we have any questions at this point? So what is the takeaway out of this entire discussion? What is the significance of this discussion? Well, we use transistors, right? Can you can we look at each individual transistor? Can we buy transistors? Are they real things that you can buy? Yep. Okay. And we only need four of those to make a NAND gate. And we know the properties of a NAND gate. We know that it is just negated and of the input. The output is the negated and of the input. Okay. Which is useless by itself because it doesn't match anything that we know, which is conjunction and disjunction or negation, not, right? But I just showed you that you can use NAND to create and also not. Okay. In the notes, it will also tell you how to make OR out of NAND. So that means right now, at this point in the semester, first class, we have already come to the conclusion that using transistors, we can make a circuit that will function like logical AND. It can function like logical OR. It can function like logical NOT. All of those logical operators that you learned from CISP 360, we can use transistors to implement every single one of those. Okay, so if you use billions and billions of transistors, you can make it do anything that you know how to do. Yes, that is kind of the whole purpose of this class. So in the next minute or so, I'm going to give you a kind of bird's eye view or satellite view of this class. Okay, so we are going to use these circuits, okay, and or not, to do arithmetic operations. In other words, addition, subtraction, comparison. You go like, what? Exactly. Yeah, we're going to do that. But before we do that, we're going to talk about base conversion. Okay. Specifically, we'll talk about some really strange base because you guys are all thinking, oh, you're going to talk about base two. Well, yes, eventually. But we'll do some really odd bases first. Like base 10. You go like, base 10? I know base 10 already. Well, by the time we talk about base 10, you will question that again. It's like, do I really know base 10? Because what I will do is I'm going to look at how we perform base 10, multi-digit addition and subtraction, extract the structure of the multi-digit mechanism, and then like, oh, look at this. You can change this one thing here, and now it will work for any base. Okay? So we'll work with really strange bases like base 7. You go like, who's going to use base 7? I'll tell you what, drunk octopi, as in plural of octopus. Why? Because it's using one tentacle to hold the beer and only has 7 tentacles left for counting, and hence it's going to need base 7. Okay, so we'll work with really odd, strange bases like base 7, and then we'll also work with base 2 because once you understand, oh, okay, so the same mechanism is going to work for whatever base we choose to use, then base 2 is like easy. Okay, but then you go like, but wait, hold on a second here. It still involves subtraction and comparison and multiplication and division and stuff like that. So when we get to base 2, we'll take a look at that special case and go like, wait, we don't need arithmetic operations here. We can turn everything into boolean operations, and or not. And then we would have achieved a way to use transistors to perform addition, subtraction, and by extension, comparison. Okay, so the class will go like that so we'll start to build larger and larger components inside the processor until we get to registers and stuff like that. And then I'll introduce the actual processor that you'll be using in this class. Most people who know people who have taken this class is going to go like, oh, okay, the x86 architecture. No, I will not use the x86 architecture. It is clumsy, it's ugly, it's just not a good thing to use. Okay, so what I'll do instead is to use my own processor architecture. Yes, I invented an architecture just so that I can teach this class the way that I want to teach this class. So that thing runs in Logisim. It is not in Silicon, it just runs in Logisim. And I have my own assembler. Okay, so the whole tool chain is already done. So we'll be writing code using that processor. What kind of code you say? Okay, you ask. Well, that processor only has 256 bytes of RAM. That's it. 256 bytes of RAM. You go like, what kind of algorithm can we possibly write with only 256 bytes of RAM? Well, I don't know. Maybe the recursive version of Fibonacci, the Tower of Hanoi. Okay, so if you're curious, you can look up those algorithms and go like, no way, we cannot code anything like that, using only 256 bytes. Yes, we can. Okay, that's what we're gonna do. In other words, by the end of this semester, you will understand everything to translate your C code, your C++ code, but I'm not going to do object-oriented programming, so just regular C. You can look at your C code and understand exactly how that translates to assembly code, what's happening in memory, the stack, and what type of instruction it translates to. And with each instruction, how does the processor get the job done? You would have the entire stack, hopefully, really clear to you by the time we end this semester. So that's the objective. Okay, that's the satellite view of this class. So do we have any questions? No. If you were to ask people from another campus, taking this class, they're not learning the same stuff. Now, is that a good thing or a bad thing? I'll leave it up to you guys to decide. I'm just gonna say it is very different the way I teach this class. Yes. Um, from what I can tell, the other campuses focus on just assembly language programming using the x86 architecture. So the downside of that is they are not really talking enough about what is inside the processor. So a lot of the options that you have in choosing what instruction or what addressing mode you need to use seems to be syntactic. Okay, it's like, oh, if I put parentheses around this, it means one thing. If I put a little asterisk in front of this, it means something else. But the reality is the architecture itself is limiting what you can and cannot do within the architecture. So in this class, that portion is totally transparent because you can actually see, oh, there's no pathway between this and this. This particular addressing mode is impossible, which means This class will help those who want to kind of lean a little bit more on computer engineering. Okay, if you want to work with NVIDIA or AMD or any other semiconductor company to come up with the next generation of GPUs for neural net computation, I think this is the way I teach this class is going to be a little bit more helpful. Okay. The other colleges also do not emphasize as much translating from C code to assembly code. So they don't talk about, oh, when you specify C code like this is really what is happening behind the scenes. They don't talk about those either. But in this class, that portion is also entirely transparent. So I think you end up learning just kind of vertically, so to speak, how things happen when your C code executes. Um, I think by the end of this semester, you'll gain a lot of understanding of that. All right. So with 5 more minutes before noon, this is typically what I do. Okay, so I'm going to open up the lab. So let me go back to here. This is awfully slow. Why is it so slow? Wi-Fi signal is not bad. Okay. Yeah, but it shouldn't matter because that's not even running on my machine. So let me see if it's just the ref. Is it an internet? Nope, it's Canvas. This is ChatGPT and it refreshed just like that. This is Canvas. So Canvas is, there we go. All right. Okay. So today's lab is down here. So I'm gonna make it visible to you. Okay, they're already configured to be due at the end of the lab session, which is 1:20 p.m. And you will need it to use an access code to do this. So the access code is Logisim itself. I'll write it on the whiteboard just in case you forget. So it's just Logisim. That's the access code. And I think I opened this from noon, so you may not be able to get into it yet. I can always just open it now. Let me let me just open it now. Available from. I mean, by the time I get this done, it's already past noontime already. So oh, available from. Oh, but that's PM. Duh. AM. There we go. Well, you still got 2 more minutes. All right, so you should be able to access the lab itself. Okay, let me go back and point out what you should see. Okay, go view as student. All right, so when you go to physical states, gates, and numbers, the third item should be the lab, which is actually in the form of a quiz, but it's not exactly a quiz because you can reattempt as many times as you want and it keeps the highest score. Which also means, for certain people who wants to use what I call the infinite monkey approach, like, just try out every single option until they get the right one, it would actually work. Now, just because that approach works does not mean it helps your understanding of the material, which I think is more important. But that's just my humble opinion. There's a companion to the lab where you upload a file, by the time you're done with the first portion. So you have to make sure that you address both of these, okay, both the lab itself and also the companion to the lab where you upload the file. All right, so I'm gonna let you guys, get started with the lab. Okay, make sure you can get in using Logisim as the access code. And then if you have any questions, I'll be here. Okay, there's no need to use the form to ask for my help because the class is small enough, it's not an issue. So any questions before you guys? No questions? All right. So I'm gonna go back to my office and drink a little bit of water. I'll be back in a few minutes. You guys can, if you want to, you can take a short break too. Oh, I need to turn off the recorder and upload the stuff.